There it is. First thing I want to do, friends, is I want to see the data. So I want to graph this data using a histogram. Slide this down a little bit. All right. So let's go to our plots. Let's turn plot 1 on. Make sure it's a histogram. And make sure it's pulling from L1 and L2, just like it has been recently, because we're talking about distributions. Make sure your other plots are turned off. I got plot 2 on. I'm going to turn him off for now. So you got plot 1 histogram. Whoops. L1, L2. Do a little zoom 9. Okay. We're going to clean that up a little bit. I hate the way that looks with the spaces. So the first thing, I want to finagle. I'm going to go to my window. X-min is 1. I can live with that. X-max is 6. It's perfectly logical, but I'm going to change it to 7. Do you remember why I'm going to change it to 7? Say that again, Athena. Yes, actually, because the first bar is going to go from 1 to 2, and that first bar is going to count the 1s. Everything greater than or equal to 1, but strictly less than 2. The next bar goes 2 to 3, it counts the 2s. 3 to 4 counts the 3s. 4 to 5 counts the 4s, and so forth and so on. So 6 to 7 is going to count the 6s. So I have to see 7 and actually see the bar. Is that fair? Now, the other thing you want to change is this X scale. Make it 1. That way the bars are exactly 1 wide. And then press graph. That's a much happier graph. So now you see this is the number of 1s we got. And you can always press trace on this too. You can press trace to see our data. There's our 41s. Our 45 2s, our 47 3s, and so forth and so on. Cool? Everybody get the graph?
Keep going so I can get the rest of those numbers.
Oh, sure. 39, 45, and 41.
Thank you.
Or 72.
Or 72, yeah.
Now, I want to go back to something Tammy brought up, which was awesome earlier. You said, what about the folks that had zeros? Which was a very, very astute thing to notice. But just like the law of large numbers predicts, they will be accounted for at some point as long as we count all 6 of them up. But what I want to drive the point home is, yeah, this happened. But Athena, you also drew something in the air about 5 or so minutes ago that looked something like this. What was that all about?
I don't remember anymore.
You drew kind of a, you were going like this. And you guys over here mentioned something that tied into that.
I don't recall anymore.
That's okay. Let me ask you a different question. Everybody go back to your stat editor. Let's suppose somebody over here said something that's sticking with me. You said you're just as likely to get a 3 as you are to get a 4, as you are to get a 5 or a 1 or a 2 or a 6. Do you guys agree with that? I think so, because this whole argument about probability up here, chance of a 3 is 1/6. Well, that's just because I chose to use 3, not because I didn't use 4 or 5. I could have put a 5 or a 6 in there. It's all the same 1/6. So in other words, if that fraction 1/6 were actually acting perfectly, how many 3s should I have gotten if that 1/6 were acting perfectly on every trial?
We should got 1/6.
1/6 of what?
6 times 6, 36.
Why 6 times 6?
Well, because you have 6 possibilities of each time you...
Right. So why 6 times 6
I guess
though?
you didn't
We only go to 1 time, right, my friend?
That's right.
Good. You are getting into joint probability. Thank you very much. We're getting to that soon. I promise. The binary distribution. I promise.
She's just way ahead of you today.
It's okay. It's okay. It's totally fine. I love it. 1/6 of what, Michelle?
Oh, I was just going to say, would it be like 17%?
Of what?
All the rolls.
All the rolls. Now, I got to add this up because I don't know how many rolls we did. We got 257 of them. So if I divide that by 6, it should be 42.83-ish. 42 5/6. So everybody, if you would, go ahead back into your stat editor and put 42.83. 42.83. 42.83. Does it bother anybody that this is a decimal? Oops. Does it bother anyone that these are coming up decimals? You can say yes, it does. You can say it pisses you off. It's totally fine.
So pissed.
You're so pissed right now. So pissed in this moment. Why is it okay to have a decimal? Why is it okay to have a decimal? Essentially, what am I looking, say that again, Lucas, nice and loud.
That's an average.
Because this is an average. You're looking now at the average, actual empirical data, on average, what you should have gotten. We're getting closer to linking up statistics to probability. This is what should have happened on average. This is what did happen in experiment. Fair enough? Notice the difference? Notice the difference? Now what I want to do is I want to look at our averages with the experimental empirical data. Okay, and this is where your graph's going to go. Yes! So here's what we're going to do. Go back to your stat plots, my friends. Go back to your stat plots. Go down to plot 2, turn her on, but use this. Don't use another histogram. The TI does a crap job of graphing 2 histograms at once. Turn on this guy, which is a line chart. It'll actually put a line over your histogram showing the tops of where the other histogram would be. And you're going to be on L1 and L3, because L3 is where your actual average datas are. And then as a mark, I usually use that mark because it's the most obvious. Then just go ahead and pick graph. Yeah, there she is.
Look at that.
Right across here. Athena, there's your beautiful graph of evenness. This is called the theoretical distribution of rolling a 6-sided die. It's called a uniform distribution for reasons you guys already pointed out. You already pointed out that the reason it looks like that is because you're just as likely to get a 1 as a 2, as a 3, as a 4, as a 5, as a 6. Now, how do you explain the differences between that and what we actually got?
Because it's a true random roll, so you're gonna get a little bit more here and there.
Good, but what happens to the more here and the less there?
The more you roll, the closer it
I love that. I love that. Hold that thought, Chester. Hold that thought. I love this. I love this. What do you notice about the bars that are above the line and the bars that are below the line?
But they're almost like you could cut them in cookie pieces and put them in.
Say that a little bit louder, Athena.
They're kind of like cookie cutter pieces. If you took the little bit and put it in that hole, it should fit, and you take the other one, it all equals up to the same amount.
Does that ring a bell from something we talked about before?
Chop, chop, chop.
Oh, good. I was thinking of a more concrete example. When I made 10 of you stand up here with lollipops.
Oh, yeah.
And I said, on average, how many do you have? And I said, you're not allowed to add them up and divide by 10. What did you have to do?
We had to give them to each other. Share.
You shared. So the bars that had more, place some here. Maybe a little bit over there. This little chop, 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 chop. Maybe place it over here. And all of a sudden, it levels out. Because the same number of observations occurs in both the purely random bars, love what you said there, purely random bars, and the not purely random bars, the perfect theoretical bar across the top. Awesome. Thank you, my friend. Thank you. Does this make sense? You guys buying this logic? Now, I want to really kind of formalize this. We got time? Yes. Oh, no, we don't. Let's take 5. Let's take 5. We're just about out of time before the break. I want to come back and formalize what we just talked about. But